I'm Josh Young. This talk is on artificial intelligence in ophthalmology, but it's really about clinical artificial intelligence more broadly. I'm a clinical professor of ophthalmology in the Department of Ophthalmology at New York University School of Medicine. My research focus is in artificial intelligence, and it is my pleasure to bring you this lecture today. These are my disclosures, none of which are pertinent to today's presentation. I've had the good fortune of being given 30 minutes to speak at this NYU conference, and in this recording, I also plan to take about 30 minutes. This is how I plan to divide it. The first nearly 1/3 of my talk will highlight recent artificial intelligence studies in ophthalmology. My second portion is going to be a bit more didactic, explaining how to critically evaluate clinical AI papers. And my third section is going to be about how to think about clinical AI. Finally, we're going to just barely touch on current FDA guidance for clinical approval of clinical AI software as a device. There's a saying that this year's artificial intelligence is next year's software. So it is incumbent upon us to define what we mean by artificial intelligence. The defining characteristic of AI is that it adapts to changing environments in order to improve its performance. Artificial intelligence need not be software, since there have been numerous demonstrations of physical objects that themselves can learn. The division between different sorts of artificial intelligence is pretty ill-defined. Still, it is worth our while to divide this large subject into three parts. In a sense, all artificial intelligence is machine learning. Ultimately, at the machine level, all artificial intelligence is mathematics. But I'm going to define machine learning as those projects that are entirely parametric, that is to say, models that deal with things like laboratory values and quantitative measurement, rather than projects that deal with images. Image recognition algorithms are sometimes referred to as convolutional neural networks, although not all image recognition uses CNN approaches. Retinal fundus images are amongst the first clinical uses of image neural networks, and there are plenty of examples. Finally, we will discuss what most people think of when they think of artificial intelligence today, and that is generative AI, large language models like ChatGPT and image recognition models like DALL-E and Midjourney. Machine learning. Machine learning is about crunching data, making predictions about different clinical measurements. Each clinical parameter is referred to in the parlance of AI as a feature, and much of machine learning is about feature selection. The algorithm looks at relationships between features, since two features in combination may be more predictive than either feature alone. The predictive ability of the model is greater than simply the combined abilities of each of its parametric parts. Machine learning is also about finding redundancies, features that are so correlated that one can be eliminated from the model, helping us find what is important in a set of laboratory, biometric, and demographic values. A recent study of ours sought to answer the question whether unrecognized ophthalmic disease can be predicted simply by looking at non-ophthalmic electronic medical record data. To do this, we employ the Optum database, initially examining 87 million patients. We identified patients with 5 extant ophthalmic diagnoses: age-related macular degeneration, visually significant cataract, diabetic retinopathy, and ocular surface disease, and then created an exact age and gender matched control group without any recorded eye conditions. Each of the groups consisted of about 750,000 patients for a total of almost 1.5 million patients. This is by any measure a big data study and probably the largest in all of ophthalmology. Between 142 and 182 non-ophthalmic parameters were examined, things like demographics and laboratory values, to build our model. In the end, we created a model that identified patients with between 2.4 and 5.7 times greater risk for the 5 pathologies examined. This means that we were able to identify patients for whom ophthalmic referral was warranted, and we did this solely based upon non-ophthalmic medical record data. Linear regression is a sort of proto-AI, and it forms the basis of a lot of machine learning. Let's build the basis for an AI algorithm that a lot of us in this audience use. These are not real data, but they are highly plausible. Generally, we use linear regression to examine correlation and to quantify a linear relationship. But we could just as easily use linear regression to separate two different populations. Unfortunately, real populations, let's say those with and without clinically significant cataracts as a function of age, don't typically lend themselves to such a clear linear border. More commonly, clinically important populations in a scatter plot require a nonlinear demarcation. This is sort of the mathematical equivalent of gerrymandering, in which we want to maximize a particular political outcome. We can imagine coming up with a regression line that is not exactly linear to accomplish this task. However, when we want to separate one population from within another population, there is no regression that will be adequate. This all seems pretty abstruse, but let's put labels on the axes, and you'll see that this is something that is highly relevant to most ophthalmologists. If we can identify a population based upon biometry that requires a particular IOL power, we suddenly have an IOL calculation formula. This AI approach is called a support vector machine. One type of support vector machine is a radial basis function, and this is what the RBF stands for in the Hill RBF formula. Let's take this one step further. What if the vertical axis were an event and the horizontal axis were time? For example, the vertical axis could be a surgical complication, and the horizontal axis could be the time of a cataract procedure. It would be enormously helpful to isolate that population who will experience complications, because if such complications can be predicted, then it would be possible to build a model that can alert the surgeon in advance of, let's say, capsule rupture. Think about it. Even if you had a 3-second warning that a capsular rupture were about to occur, that would be sufficient time to avoid it. Such a surgical model does not yet exist for ophthalmology, but models have been built in other surgical contexts, in this case for cardiothoracic surgery. Before the advent of large language models, the most impressive AI projects were those demonstrating image recognition. In clinical medicine, image recognition, segmentation, and labeling are still the most relevant, although this is likely to change soon. Image recognition is conducted by means of neural networks, particularly convolutional neural networks. The image is linearized, that is to say, all the pixels are lined up in a single row. The row is then simplified, that's the convolution, and then passed through a number of hidden layers before being fed into an output layer that labels the image. All of the FDA-approved ophthalmology AI products to date are image recognition systems. In fact, all are diabetic retinopathy recognition systems, although other products have received provisional approval. The performance has been outstanding. Now, I want to draw your attention to the first 2 bullet points. The first is the enormous number of images required to build the system. The second bullet point highlights the most relevant use case for this sort of model. I'll explain. The sensitivity for glaucoma, AMD, and diabetic retinopathy is impressive, but what is the use case here? Is this model going to displace ophthalmologists? Absolutely not. The most relevant use case here is the detecting of patients for referral. Here, the model can be installed in a clinical setting without ophthalmologists, let's say a rural diagnostic center, to determine which patients should be referred. One important use case for AI image recognition is the interpretation of novel diagnostics. It can, in a sense, hold the clinician's hand while she or he is learning how to use and interpret the output of a new diagnostic device. On November 30th, 2022, the world shifted on its axis. November 30th, 2022 was the day that ChatGPT was released to the public. Large language models, LLMs, and other forms of generative AI are now almost synonymous with artificial intelligence. I know I do not have to explain what LLMs like ChatGPT, Gemini, and Grok are. I also don't have to explain DALL-E, Midjourney, and Sora, although you may not recognize these by name. They are the AIs that generate images and videos that can be employed, for example, to generate deep fakes. Generative AI is in its infancy, but infants in AI tend to grow up fast. Some of the early implementations are for patient interaction, particularly explaining clinical conditions to patients. There are a number of large language model-based telephone patient interfaces. One of them, Dora, is in clinical use in a number of NHS hospitals in the United Kingdom, in which it conducts audio telemedicine visits with patients who have had uncomplicated cataract surgery. When Dora finds the conversation drifting out of scope, that is to say, when a patient is describing something that is not entirely routine, Dora connects the patient with the ophthalmologist's office. Otherwise, the visit is conducted entirely by the AI, which then generates documentation for inclusion in the patient's chart. Generative AI, in its capacity to create images, can serve an important role both in training and as an assistant to other AIs. Remember a few slides ago in which we saw a model capable of diagnosing referable diabetic retinopathy? That model had been trained on more than 70,000 images. That's doable for diabetic retinopathy, but it's not possible for rare retinal conditions. Even conditions that are not super rare, like Best's disease, this number of images is not possible to obtain. Does this mean that image recognition AIs will never be able to be employed to recognize these rarer conditions? Image creation AIs can be used to produce retinal photographs. These are, in essence, deep fakes of retinal pathology. The newly generated retinal images then need to be reviewed by experts, that's to say retinologists, to determine whether they are plausible and show the pathology of interest. This is really not any different from traditional image recognition for retinal photographs of actual patients. Genuine photographs also need to be reviewed by experts who then label them as having the pathology of interest or of being controls. It is the labeling by experts that determines what we call ground truth. These experts can just as well create ground truth based on retinal deepfakes. If the images are not plausible, the experts will reject them. In the end, the synthetic data may be generated that can be used to train image recognition models now capable of recognizing rare conditions. These images can also be used for training residents to improve their own image recognition. To my mind, this is the most important part of my talk. None of us reads clinical papers non-critically. We know what to look for when evaluating the importance of a clinical paper and to what extent we should let it influence our own practice. We look for things like correlation, and we're used to seeing these sorts of scatter plots. When we read papers, even excellent ones like this one with unimpeachable authors, our eyes are still drawn to p-values and n's. But AI models are fluid, and once a model is created, the end can be limitless. Our traditional methods of critically evaluating papers do us no service in evaluating the utility of an AI project. This is a traditional study, not artificial intelligence, that can serve as a gateway for us to understand clinical AI. This is a comparison of OCTA to fluorescein angiography in identifying choroidal neovascularization. In this study, fluorescein angiography is taken to be the gold standard in OCTA, the modality being tested. The question is whether OCTA can be as accurate a tool as fluorescein angiography for identifying a particular pathology. The measures here are sensitivity and specificity, and the results are shown in a 2x2 matrix in which the upper left-hand corner, the 33, shows true positives, and the lower right-hand corner, the 59, shows true negatives. The upper right-hand corner shows false positives, and the lower left-hand corner false negatives. This sort of chart is called a confusion matrix. Now imagine that rather than using the term gold standard, we use the term ground truth. The two are essentially interchangeable. 2x2 confusion matrices are appropriate for binary conditions, pathologies that are either present or not present. But matrices can be larger if the pathology can be staged to be ordinal. This is a confusion matrix for an image recognition AI in which the ground truth is shown in the vertical axis and the AI's prediction in the horizontal axis. Ideally, the diagonal from upper left to lower right should have the largest values. In the case studies I presented at the beginning of this lecture, you saw a lot of graphs that looked like this. These are receiver operating curves, and they are the essence of evaluation of AI models. To understand them, let's create a diagnostic test of our own. This is a 20-sided die, and I have no idea what these are used for in the real world. We are going to use it to detect keratoconus. Now, let's imagine that we are testing this new diagnostic device on a population of patients, half of whom have keratoconus. We are going to diagnose keratoconus by rolling this die once for each patient. In order to make the diagnosis, we are going to create a rule that if the number of the die is greater than n, then we will say that the patient has keratoconus. And if the number is less than n, we are going to call the patient normal. If we set our n at 0, since the 20-sided die has no 0 side, regardless of the outcome of the roll, we are going to say that the particular patient has keratoconus. That is to say, the likelihood of normal would be 0. By setting 0 as our threshold, we're going to correctly diagnose every single keratoconus patient. Of course, we're also going to incorrectly diagnose every normal patient. The threshold will give us 100% sensitivity, but the worst possible specificity. What if we set our threshold at 10? Then we will correctly diagnose only half of the keratoconus patients and incorrectly diagnose only half of the normal patients. We will have a 50% sensitivity and a 50% selectivity. Still pretty bad for a screening test. This graph of a straight diagonal line from lower left to upper right is what we would obtain by pure chance. This is the same graph, but now I've normalized the axes so that they go from 0 to 1. I could have labeled the axes true positives and false positives, or sensitivity and specificity, and the shape of the graph would be the same. This would allow us to compare our model to models from other studies, because in the papers you read, you will see the axes labeled true positives and false positives, or sensitivity and specificity. We call this a receiver operating curve, or ROC. This is an actual receiver operating curve from the model that recognized patients at high risk for undiagnosed ocular pathology based only on non-ophthalmic medical record data. This particular curve shows the diagnosis of type 1 proliferative diabetic retinopathy. The receiver operating curve has an axis of true positive and a false positive, that's to say of sensitivity and of specificity. Since the curve is continuous, there's no intrinsic threshold, no model value that tells us definitively where it believes the patient has got PDR or not. However, by examining this curve, we see that there is an elbow, a place where the curve drops off or levels out depending upon which direction you're looking at the graph. This is the obvious place for a threshold, a value generated by the model that will optimize specificity and sensitivity. This is one important utility of the receiver operating curve. This again is our receiver operating curve for our 20-sided dye keratoconus detector. We already know that this is a terrible diagnostic test because we don't diagnose any pathology by rolling dice. But let's see if we can do things a little bit more quantitatively. I have shaded the area under the receiver operating curve. Let's do a little math. What is the value of this area? Did you get it right? Under the value under this curve is 0.5. In fact, 0.5 is the area under the receiver operating curve that represents a purely random result. The area under the receiver operating curve is called the AUROC or OROC, or more commonly just AUC for area under the curve. If we know that an AUC of 0.5 is poor, then what is a good AUC? What AUC represents a model that is good at making predictions? These are examples of receiver operating curves, and in the lower right-hand corner, the area under these curves. A perfect classifier is shown in blue, and of course would have an area under the curve of 1.0. A good classifier may be somewhere in the 0.8s, and a bad classifier is one that would be more similar to a roll of dice with an AUC close to 0.5. Evaluating generative AI is a lot more difficult. Probably the biggest concern with generative AI is that it makes things up. If you press ChatGPT for a reference, it'll give you one. It just may give you one that does not exist, one that it has made up. In the parlance of AI, we say that the large language model has hallucinated that reference. I use large language models frequently in the context of my own research. I ask for references, but then I check to make sure that the references exist and that they actually say what chat says that they do. This checking is a hassle, but it's not difficult. The danger is that a large language model engaging in a conversation with a patient could also begin to make things up. It may mislead the patient and result in an undesirable outcome, and this will be very difficult to detect until the conversation is reviewed. The metric that you will see in scientific papers is the model's hallucination rate. However, depending upon how it is measured, the hallucination rate, particularly for references, can vary between 20% and 80%, and of course it changes every time a new model is introduced. I want to spend this last portion of my talk discussing how we should think about AI. When AI gives problematic results, it is rarely because the algorithm or the training process is flawed. It is because the training data is biased. This is a story that predates modern AI. In the mid-1980s, expert decision software existed, but it failed to exhibit what people at the time called common sense. To address this, a project called CYC was created. CYC, from the word encyclopedia, would ingest the contents of encyclopedias and then make common sense conclusions from the information it gathered. And what do you think the conclusion was that CYC drew after ingesting all this material? And it wasn't wrong. Absolutely everybody in the encyclopedia is famous enough to be in an encyclopedia. The problem was not with the methodology, it was with the training set. Let's try a little experiment of our own. I'm going to do something anathema to conference lecturers. I'm going to ask you to take your phones out and to open up a web browser and go to Google. Type in women are and look at the autocomplete suggestions that Google gives. Are they the same as mine? I bet they're not. Even though you and I are accessing the same Google autocomplete engine, why is there a difference? It is because your autocomplete and my autocomplete are trained on different training sets. The result is that the outcomes are biased. We usually think of bias as something to be avoided, but there's really no difference between biased and customized. However, although my autocomplete works especially well for me, my autocomplete will not work as well for you. The model on my phone is not generalizable. Generalizability of models is a big topic in artificial intelligence, and it is not one with an obvious goal. If we create a model that works well for the NYU Department of Ophthalmology, but not as well elsewhere, should we compromise its performance here just to make it more generalizable? Should we build models that are inclusive of ethnic groups not present in our own population? In order to address the question of generalizability, we must necessarily define the market, the population on whom this model will be deployed. We should also keep in mind that AI models do exactly what we ask them to do, even if it's not exactly what we want them to do. In this case, an AI model was trained to distinguish wolves from dogs. It did an absolutely fantastic job. Only, it turned out that all the training photos of wolves had snow in the background. The model was simply detecting the presence of snow. We need to be very careful with image recognition models that the portion of the image being recognized is the portion that is important clinically. One way of doing this is through the use of what is called heat maps, illustrations of the algorithm's region of focus to make sure that these align with our region of clinical interest. This to me is super interesting. This is something that I discovered in discussion with ChatGPT about how it works at an algorithmic level. Large language models like ChatGPT are sometimes described as massive and glorified autocomplete algorithms, such as we saw with our Google search. At its core, large language models divide your query, but not exactly by word in the way that Google autocomplete does. Rather, it divides your query into what are called tokens. Tokens are typically about 4 characters long, but can vary, and tokens will often split words. This is a tokenization example in which my question consists of 12 words, but has been broken up into 15 tokens. Here I've had ChatGPT, I've given ChatGPT a query in Chinese, and it has tokenized this query. Chat will create its answer, its autocomplete, based on these tokens. It will autocomplete my Chinese query based on the Chinese text samples on which it has been trained. Now, here's the interesting thing. The Chinese literature in the training data is not a translation of the English literature. It is native Chinese literature. Also note that ChatGPT did not translate my Chinese query into English before tokenizing it. This means that if I ask a question in Chinese, the answer it will give will be based upon Chinese publications and websites and the like, not upon Chinese translations of English literature. But what if the Chinese clinical literature is different in content from the English clinical literature? If I ask a question in Chinese, will it give a different answer? I'm sure you know there are all sorts of guardrails on large language models to prevent your using it as a physician. And there are ways to get around these guardrails. In order to get an answer, I presented ChatGLM, a Chinese large language model, with the clinical presentation as if I were using that presentation for an exam in order to prompt it to give me a clinical answer. This is the question I gave, and these are the first 5 entries in its differential diagnosis. Now, I don't show you this to critique the differential that ChatGLM is giving. I just want you to look at this differential. Then I use Google Translate to ask the identical query in Chinese, and you will note that the differential diagnosis is different. This is a result of language-specific tokenization and autocompletion. Which differential diagnosis is correct? Maybe the English corpus of ophthalmic literature is larger than the Chinese and it is the more appropriate differential, but maybe they're both correct. Maybe the Chinese differential diagnosis reflects the Chinese literature and is biased towards the Chinese patient population and more reflects an appropriate differential diagnosis for that population. I'm not passing judgment, but I am calling attention to the fact that the language in which you ask a question will influence the answer. If I were to have spent all 30 minutes of this lecture discussing FDA guidance, it would still not be enough time. I just want to give you a flavor of the problem. It is not only that AI is advancing so quickly that it is impossible for regulators to keep up, but it is in the nature of AI itself not to be static. The FDA has taken an approach it calls Predetermined Change Control Plan, or PCCP. This requires periodic re-examination of approved AI models. Let me give you an example of why this is important. Let's say our model detecting unrecognized ophthalmic pathology from non-ophthalmic medical records were deployed. Most patients don't have unrecognized ophthalmic pathology, but some do, and the model performs brilliantly and suggests referral of high-risk patients and diagnoses are made. These patients would then no longer have unrecognized ophthalmic pathology. How would this change the population? What does this population look like now? It has a far lower number of patients with unrecognized pathology, but more importantly, it is a different population from that on which the model was trained. Is the model still going to be accurate with this new population? We don't know. We would have to retest. It is the model's own success that results in its subsequent inaccuracy. Hence the need for periodic re-examination and a plan to assess drift. I'll leave you today with the images of these two handsome men. For the image on the left, I asked ChatGPT, based on our conversations, to make a picture of itself if it were a person. For the image on the right, I asked ChatGPT what it thinks I look like.